On the morning of November 10th at precisely 04:02 Coordinated Universal Time, one of the most powerful solar flares of this entire cycle erupted from the surface of our star. Classified as an X2.6 class flare, this event marked a turning point in what had, until that moment, been a relatively stable week for space weather. The flare originated from active region 3491, a sunspot cluster located near the centre of the solar disk, placing it in an almost ideal position for Earth-directed impact. Within seconds, space weather monitors began to register sharp spikes across multiple wavelengths of radiation, including the X-ray spectrum, ultraviolet, and even soft gamma emissions. But what made this moment so crucial was not just the power of the eruption, but the fact that it was aimed directly at our planet. For scientists working in solar observatories around the world, from Boulder in the United States to Meudon in France, this wasn't just another solar flare. It was a warning shot from a magnetically unstable region that had already shown signs of increased complexity in the previous 48 hours. In fact, 2 days earlier, the same region had produced a smaller M5 class flare, which had already caused minor radio blackouts in parts of the southern hemisphere. But nothing in those earlier outbursts compared to what was just unleashed. The X2.6 flare released more than 1 billion trillion joules of energy in less than 5 minutes. To put that in perspective, that's over 1 million times more energy than the most powerful nuclear weapon ever tested on Earth. The effects were immediate. High-frequency radio blackouts occurred across the Pacific Ocean basin, especially affecting aviation routes connecting Asia and the western coast of North America. Flight dispatchers were forced to reroute aircraft away from polar paths to minimize communication loss. Meanwhile, power grid operators across high-latitude regions entered active standby mode, preparing for potential geomagnetic interference in the hours to follow, and within the space science community the attention turned quickly to what the flare might have launched alongside its radiation, a coronal mass ejection, or CME. Unlike a flare, which is an intense burst of radiation, a CME is a cloud of magnetized plasma, and it moves slower, but with lasting consequences. Early coronagraph imagery from the SOHO and Stereo A spacecraft revealed the flare had indeed triggered a CME. What was unexpected, however, was the speed. Estimates showed it was moving at over 150 kilometers per second, making it a strong candidate for Earth impact within 24 to 36 hours. Simultaneously, ground-based magnetometers began picking up subtle fluctuations, hinting that the interplanetary magnetic field was already beginning to respond to the flare. The solar wind density increased. Low-frequency radio observations showed enhanced scattering from the upper layers of Earth's ionosphere, and aurora watchers in Canada and Scandinavia were already preparing for increased activity in the coming nights. But perhaps the most surprising detail came not from Earth, but from the 3i Atlas probe, still trailing Earth's orbit at a wide angle. Just moments before the flare, Atlas registered an unusual magnetic flux rope disturbance in the corona, a prelude to what was about to happen. It's one of the first times in recent history that an interstellar probe caught solar eruption precursors from such an oblique vantage point. The X2.6 class flare of November 10th wasn't just a burst of energy, it was the beginning of a sequence, a harbinger of more to come. And for the scientists who study solar dynamics, this moment opened a window, not just into the sun's behavior, but into Earth's vulnerability beneath it. The first flash had occurred, and it would not be the last. Just 13 minutes after the first X2.6 class flare had shaken the solar observatories into alert mode, the Sun released a second event, smaller in scale but no less significant in its implications. At 04:15 Coordinated Universal Time, active region 3491 erupted again, this time producing an X1.4 class flare. This second pulse was not just a continuation of the solar instability, it was the start of something more complex, a sequence of eruptions, stacked closely in both space and time, with the potential to merge and amplify each other as they raced outward into the solar system. In isolation, an X1.4 flare would already be considered an intense event. It ranks among the highest category of solar flares, capable of disrupting communications, energizing Earth's radiation belts, and triggering visible auroras far from the poles. But in this context, so soon after the first and from the same sunspot cluster, the second flare signaled an escalation. Not only had active region 3491 failed to stabilize after the first release, but its magnetic complexity had increased. This suggested a cascading failure within the sunspot's internal structure, a magnetic reconfiguration that could result in further eruptions in the coming hours or days. While the first flare's accompanying coronal mass ejection was already in flight, this second flare appeared to launch its own CME, moving even faster. Preliminary measurements from the Stereo A spacecraft indicated a velocity exceeding 1/800 km per second, which is exceptionally fast for solar plasma. Even more crucially, the trajectory of the second CME appeared to follow directly behind the first, creating a condition that space physicists refer to as CME cannibalization, where a faster CME overtakes a slower one, compressing and amplifying the magnetic field and particle density in the space between them. This interaction zone becomes more than just a sum of its parts. It forms a compressed region of turbulent magnetic flux, with elevated energetic particle concentrations and a sharper shock front. When such a compound structure reaches Earth, it can trigger geomagnetic storms that are far stronger than either CME could cause alone. In essence, the second pulse didn't just echo the first, it transformed it. Back on Earth, space weather models had to be rapidly updated. The NOAA Space Weather Prediction Center, which had already issued a G2 watch based on the first event, now raised the potential to G3 or higher. Operators of satellites in low Earth orbit and medium Earth orbit began initiating protective protocols, switching vulnerable systems into safe mode and delaying non-essential data transmissions. But not all effects are delayed. As with the first flare, this second event immediately flooded Earth's upper atmosphere with high-energy X-rays and ultraviolet radiation. These waves interact with the ionosphere, the electrically charged layer of Earth's atmosphere that enables long-distance radio communication. Within minutes, there were confirmed reports of radio signal degradation across the Indian Ocean and parts of East Africa, where the sunlit side of the planet was directly exposed. Aviation crews on polar routes were advised once again to monitor HF communication stability, and several airlines began planning for reroutes if the situation escalated. At the same time, researchers began analysing whether this second event carried a different magnetic polarity, a factor that could determine how efficiently it couples with Earth's magnetic field. Perhaps most strikingly, scientists at the South African Radio Astronomy Observatory noted that the second flare also triggered a response from the 3I Atlas probe, still recording background solar behaviour. The probe's magnetometers detected a second oscillation, slightly lower in amplitude than the first, but closer in frequency to predicted flux rope detachment models. It suggested that the Sun's magnetic field was entering a state of prolonged instability. The second pulse confirmed a pattern. This was no isolated flare, no fluke. It was the signature of a sunspot region entering a hyperactive phase, with magnetic fields unravelling in rapid succession. And with both CMEs now in transit, one chasing the other, the story of November 10th had officially become something Earth had not seen in years, a double threat racing across space. By 0520 Coordinated Universal Time on November 10th, the early hypotheses became a certainty. Both flares, the X2.6 and the X1.4, had launched powerful coronal mass ejections, and both were now confirmed to be Earth-directed. The flare pair had created what space weather scientists call a double CME event, a scenario that is rare, complex, and potentially dangerous. While individual CMEs can pose risks to satellites, power grids, and communication systems, two CMEs launched in close sequence can interact in ways that multiply those risks. The first confirmation came from coronagraph images captured by the SOHO spacecraft, which monitors the Sun from a stable, positioned between the Earth and the Sun. Its LASCO C2 instrument showed a full halo of ejected plasma expanding outward from the solar disk. A full halo means the ejection is heading either directly toward or away from Earth, and based on timing and flare coordinates, this one was clearly inbound. Just minutes later, data from Stereo A, which orbits ahead of Earth in its orbit, captured a second halo, slightly brighter, denser, and faster. Scientists at NOAA and ESA began cross-comparing datasets, and the trajectory models quickly converged. Both CMEs were not only Earthbound, they were travelling along nearly the same trajectory. The second was moving roughly 600 km per second faster than the first, making it almost certain that a merger would occur somewhere between the Sun and Earth. This is where things get complicated. When two CMEs interact in space, their magnetic fields can combine, cancel, or amplify each other, depending on their orientation. If the two CMEs have aligned southward magnetic fields, which is the configuration most likely to penetrate Earth's magnetosphere, the resulting compound storm can create conditions far more intense than either CME would have triggered alone. Even if they don't fully merge, the compression zone between them becomes a region of heightened turbulence, denser plasma, and chaotic magnetic flux. The term CME cannibalization is often used to describe this phenomenon. The faster second CME acts like a predator, swallowing the tail of the slower leading cloud. In doing so, it compresses the magnetic field lines ahead of it, creating a sharper shock front. This interaction can also trap energetic particles between the two clouds, leading to sustained high radiation levels that can linger long after the initial impact. By midday UTC, space weather modelling centres had issued updated predictions. The first CME was expected to arrive at Earth between 17 DIAD and 21 UTC on November 11th. The second, riding in its wake, was projected to arrive less than 6 hours later. The window for impact was narrowing, and the time between impacts was too short for the magnetosphere to reset. Data analysts across multiple agencies, including NASA, NOAA, ESA and JAXA, worked in parallel to update threat forecasts. The models began to reflect the increased probability of a G3 or G4 geomagnetic storm, with a possibility of reaching G5 if the merged magnetic structure aligned just right with Earth's magnetic field. Meanwhile, the 3I Atlas probe, positioned at a unique angle relative to Earth and the Sun, continued transmitting data on the interplanetary medium. The probe's instruments picked up density gradients consistent with two distinct CME fronts, and a third zone of compression developing between them. It was one of the clearest observational confirmations of a double CME event in progress, captured in real time by an interstellar object still within monitoring range. To most of the world, space remained quiet. But to the silent instruments watching the Sun, the message was deafening. Earth was about to face not one, but two consecutive waves of solar plasma, packed with magnetic force, moving faster than almost any storm this solar cycle, and the gap between them, that narrow turbulent corridor, might turn out to be the most dangerous zone of all. As the twin coronal mass ejections raced away from the Sun, a new structure began to form, one that could not be seen directly, but would soon be felt across Earth's magnetic field. These were shock fronts, invisible walls of compressed solar plasma travelling through space at supersonic speeds. While CMEs themselves are massive clouds of magnetized particles, it is often their leading edges, their shock fronts, that deliver the most immediate and intense impact when they encounter the space around Earth. To understand how shock fronts form, imagine the CMEs as speedboats cutting through the still waters of the solar wind. The faster they travel, the more solar plasma they push ahead of them. This creates a bow shock, a sudden change in density, speed, and magnetic field strength. In space, these transitions are not gradual. They arrive as sudden impulses, sometimes in less than a minute, and can trigger intense reactions in the magnetosphere, even before the bulk of the CME arrives. In the case of the November 10th events, both CMEs were travelling at extreme velocities. The first moved at over 150 km per second, while the second approached 1,800 km per second. These speeds far exceed the normal flow of the solar wind, which averages around 400 km per second. As a result, both ejections were generating their own independent shock fronts, and the space between them was beginning to fill with compressed, turbulent plasma. The Deep Space Climate Observatory, DESCORV, and ACE spacecraft, both positioned at the L1 Lagrange point between Earth and the Sun, began detecting the early signs of these fronts. Proton density in the solar wind increased rapidly. The magnetic field vector began to oscillate with growing amplitude, and most notably the plasma beta, a ratio that measures how much particle pressure dominates over magnetic pressure, began to spike in short, irregular bursts. These are textbook indicators that a shock structure is moving closer. Meanwhile, back on Earth, ground-based magnetometers prepared for what's known as a sudden impulse, a sharp, abrupt spike in geomagnetic field strength that occurs when a shock front hits the magnetopause. This impact compresses Earth's protective magnetic shell, pushing it inward by thousands of kilometers. For satellites in geosynchronous orbit, this can mean a temporary loss of shielding from charged particles. For astronauts aboard the International Space Station, it can mean a shift in their exposure to cosmic radiation. But what made the November 10th event especially rare was the interacting geometry of the shock fronts. As the second CME began to overtake the first, it wasn't just closing the gap, it was colliding with the trailing edge of the first plasma cloud, pushing a new shock wave through an already turbulent medium. This set up the conditions for what physicists call a compound stream interaction, a type of shock fusion that can temporarily increase particle acceleration, density gradients, and electromagnetic pressure in ways that are difficult to model in real time. The resulting environment is extremely dynamic. Spacecraft exposed to it can experience multiple changes in magnetic orientation, known as magnetic discontinuities, which may cause unexpected behavior in onboard electronics. Solar energetic particles trapped in the region between the two shocks can be flung outward in all directions, some of them reaching Earth even before the CME bodies arrive. Perhaps most concerning is that these shocks act as triggers for geomagnetic storms. If the shock carries a magnetic field oriented southward, opposite to Earth's northward field, it can unlock the magnetosphere, allowing solar plasma to pour in. This is when geomagnetic storms intensify rapidly, producing auroras, voltage fluctuations in power lines, and sudden ionospheric disturbances that affect GPS and communications. As the compound shock structure neared Earth, scientists at the South African Radio Astronomy Observatory noted that even the 3I Atlas probe, far from the main action, registered a sudden jump in background proton velocity. Though distant, Atlas provided an oblique confirmation. The solar wind had changed, and the shock was real. Invisible to the eye, but undeniable in effect, the twin shock fronts were now converging, not just on Earth's position, but on the delicate balance of systems that power modern civilization. In the hours leading up to the twin solar eruptions of November 10th, one object, far removed from Earth and silent to the public eye, began registering something strange. The 3I Atlas probe, positioned in an outbound orbit after its perihelion pass, was no longer just a passive observer of interstellar chemistry. It had become a frontline sensor for changes in the Sun's deeper structure, and what it detected just before the first X 2.6 class flare has since drawn the attention of scientists across 3 space agencies. The detection began quietly. At 0316 Coordinated Universal Time, approximately 46 minutes before the first solar flare, 3I Atlas logged a subtle but measurable shift in the interplanetary magnetic field at its location. The field vector didn't spike violently. It began to oscillate. A rhythmic pattern of high-frequency waves centered near 1.2 MHz began to rise above background levels. At first, the data was treated as noise, a minor flux, possibly from a distant microflare or routine solar turbulence. But then came the second anomaly. Approximately 5 minutes later, the probe's Langmuir plasma sensor registered a sudden drop in electron density, paired with a sharp increase in ion temperature. This kind of inverse coupling typically indicates a change in energy transfer efficiency within the plasma environment. Put simply, the solar wind wasn't just getting faster, it was getting hotter and more structured, and the timing couldn't be ignored. This all unfolded less than an hour before the first flare erupted. For scientists analysing the data in hindsight, these pre-flare signals pointed to an early destabilization of the solar corona, something that standard near-Earth instruments failed to capture. Because while Earth-orbiting satellites like GOES-16 and SDO monitor the Sun's face, 3I Atlas was angled off-axis, positioned nearly 8 degrees behind the Sun-Earth line, with a partial lateral view of the Sun's surface activity. This unique vantage point allowed Atlas to sense the magnetic pressure buildup from a different angle, potentially identifying the formation of a flux rope, a twisted bundle of magnetic field lines that often precedes a major coronal mass ejection. Flux ropes are notoriously hard to detect directly, but their signatures can appear indirectly through what plasma physicists call precursor perturbations, background changes in density, pressure, or wave structure that suggest a region is preparing to release stored energy. That's exactly what Atlas recorded. Roughly 12 minutes before the X 2.6 flare, the probe's energetic particle detector captured an upward shift in proton energies, with a small but distinct tail extending into the greater than 10 megaelectronvolt range. These are not particles that cause damage on Earth, but they are the early runners of something larger. Known as solar energetic particle precursors, These signals often arrive minutes or even hours before a full flare or CME, offering one of the only predictive glimpses into solar dynamics. But Atlas saw more than just energy levels. Its magnetometer logs indicated a mild rotation in the ambient field direction, one that matched the rotation typically seen when coronal loops destabilize. These loops, made of arching magnetic lines anchored to the sun's surface, often twist and stretch under stress until they snap, flinging plasma into space. The field rotation was not large enough to confirm a loop collapse, but it fit within the threshold for a pre-eruption magnetic reconfiguration. All of this paints a picture of what Through-Eye Atlas became in those final quiet moments before the storm, a listening post on the frontier of heliophysics. A probe not originally built for space weather monitoring, but perfectly positioned to observe one of the most complex solar events of the year. Scientists now believe that had Atlas not recorded these early waveforms, the dual flare sequence would have arrived without warning. Its data has already been forwarded to both ESA's Space Weather Service network and NASA's Heliophysics System Observatory, where it's being incorporated into models to better forecast flare onset signatures from unusual angles. In a solar system where most observatories look head-on, Three-Eye Atlas looked sideways, and in doing so may have given us the very first whisper of a warning that the sun was about to speak in full force. When a single solar storm reaches Earth, the effects can already be profound. Charged particles crash into the magnetosphere, triggering auroras, radiation storms, and disturbances in GPS, radio, and satellite systems. But when two solar storms are launched in rapid succession, as happened on November 10th, the danger doesn't just double, it compounds in ways that are complex, volatile, and far more difficult to predict. To understand why two solar storms are worse than one, we first need to explore how coronal mass ejections, or CMEs, behave as they travel through the solar system. Each CME is a massive bubble of plasma and magnetic field launched from the sun's outer atmosphere. It carries with it billions of tons of energized particles, all embedded within a magnetic structure that can extend over tens of millions of kilometers. As it moves, it distorts the solar wind and can even reshape the interplanetary magnetic field in its path. The first CME from the November 10th eruption, associated with the X-2.6 class flare, was already intense. But just 13 minutes later, the Sun launched a second CME, tied to an X-1.4 class flare, from nearly the exact same region on the solar disk. This second ejection was faster, more compressed, and quickly began to catch up to the first, a phenomenon known as CME cannibalization. Here's what happens when one CME overtakes another. First, the space between the two plasma clouds becomes a zone of compression. Instead of letting the first CME gradually expand into interplanetary space, the second CME slams into its tail, squeezing the magnetic field lines and amplifying particle density. This creates a turbulent high-pressure zone with chaotic magnetic structure, a perfect setup for unpredictable interactions once it reaches Earth. Second, the magnetic orientation of each CME plays a key role. If one storm carries a northward magnetic field and the other a southward field, they might partially cancel each other out. But if both carry a southward orientation, they align perfectly with the direction that allows maximum energy transfer into Earth's magnetosphere. This opens the door wide, allowing a much more violent coupling with our planet's protective magnetic shield. It's not additive, it's exponential in its impact. The third risk lies in timing. Earth's magnetosphere is not a rigid shell. When the first CME hits, it compresses the magnetic field, causing geomagnetic storms and triggering auroral displays. Normally, Earth would begin to recover after such a hit. But when a second CME arrives before that recovery is complete, it strikes an already weakened, agitated system. This can lead to longer storm durations, higher geomagnetic indices, and far more intense energy transfer into the atmosphere and ionosphere. During the November 10th event, space weather models began forecasting a potential G4-class geomagnetic storm, one level below the most extreme classification on the scale used by NOAA. This isn't just a theoretical concern. In past double CME events, such as the 2001 Bastille Day storms or the Halloween storms of 2003, the cascading effects caused widespread disruption. Power grids overloaded, satellites failed, even pipeline currents fluctuated enough to trigger alarms. Another concern with sequential storms is their effect on satellites and spacecraft. The first CME often strips away part of Earth's upper atmosphere, increasing drag on satellites and exposing sensitive electronics to heightened radiation. The second CME, arriving with even more energy, finds satellites in a more vulnerable state. It can trigger single-event upsets, corrupt memory, and even damage solar arrays. Finally, the psychological and operational strain on ground teams must be considered. Solar storm protocols, from space agencies to airline route planners to electrical grid operators, are designed for isolated bursts. A two-stage storm compresses response time and overwhelms real-time monitoring systems, creating windows of uncertainty where critical decisions must be made with incomplete data. In short, two solar storms are not just twice the problem. They create a complex system of magnetic interaction, particle acceleration, and cascading physical effects that can reshape the near-Earth environment for days. When one storm hits, Earth braces. When two collide and come together, the system bends, and sometimes it breaks. By the evening of November 10th, scientists around the world were focused on one thing: the arrival window. With two powerful coronal mass ejections now confirmed and racing toward Earth, attention turned to timing. When would they arrive? And more importantly, how much warning would we have? The answer, as always with space weather, was layered in uncertainty. Coronal mass ejections, or CMEs, are not point-like objects. They are immense clouds of solar plasma, often millions of kilometers wide with irregular asymmetrical shapes. Their leading edges can be sharp or diffuse, depending on the density of the ejector and the ambient conditions in the solar wind. As a result, predicting their exact arrival time at Earth is more like forecasting a fog bank than a freight train. Still, thanks to a growing network of observational instruments both in space and on Earth, scientists were able to narrow the estimates. The first CME, associated with the X-2.6 class flare, was expected to arrive sometime between 17 and 21 hour Coordinated Universal Time on November 11th. Its velocity, measured at over 1,150 km per second, placed it among the faster CMEs of this solar cycle. But CMEs rarely travel at a constant speed. They interact with the solar wind, slow down slightly due to drag, and can be deflected by other structures in the interplanetary medium. These variables introduced a margin of uncertainty of several hours. The second CME, tied to the X-1.4 class flare, was even faster, clocking in at nearly 800 km per second. And because it was launched just 13 minutes after the first, it was predicted to catch up within 36 hours. This meant that instead of two distinct impacts, Earth would likely experience a merged arrival, or a two-step storm with very little time in between. From a scientific perspective, this posed an incredible challenge. Standard warning systems like the AC and Dieskova spacecraft at the L1 Lagrange point typically detect an incoming shockwave between 30 and 60 minutes before it reaches Earth. These satellites measure solar wind density, velocity, temperature, and magnetic field, offering real-time insights into the structure of the arriving cloud. But they cannot see beyond their immediate surroundings. If two CME fronts arrive within a short time span, especially if the second arrives while the first is still compressing the magnetosphere, the warning systems may become overwhelmed or miss the onset of the second wave. Analysts were already preparing for this possibility by closely monitoring shock signatures, sudden impulses, and changes in the interplanetary magnetic field direction. The importance of the IMF orientation during arrival cannot be overstated. If the incoming magnetic field is aligned northward, it resists entry into Earth's magnetosphere. But if it is southward, it connects directly to Earth's field lines, allowing energy to pour in. The models based on coronagraph data suggested the merged CME structure was likely to contain long-duration southward fields, a setup that could lead to sustained geomagnetic storming for several hours, or even longer. By midday, on November 11th, the SWPC, Space Weather Prediction Center, issued a G3 level geomagnetic storm watch, with the potential to upgrade depending on real-time observations. Power grid operators in Scandinavia, Canada, and parts of the northeastern United States were advised to monitor line currents. Airlines began preparing for possible polar reroutes, and aurora forecasts shifted, extending visibility ranges as far south as Oregon, Germany, and northern Japan. In a separate alert, ESA's Space Situational Awareness Program advised satellite operators to begin orbit adjustments or prepare for heightened radiation exposure. Atmospheric drag in low Earth orbit was expected to increase by up to 30%, potentially affecting objects like Starlink satellites and weather payloads. For the general public, the storm's arrival might be signalled by dazzling auroras or temporary GPS glitches. But for the scientific community, this was a precise, high-stakes countdown. The window was open, 2 storms were inbound, and Earth, suspended in the path of charged particles and magnetic pressure, waited. When a solar storm reaches Earth, it doesn't strike with brute force alone. What determines how deeply it penetrates and how much disruption it causes depends on something far more subtle. The orientation of the interplanetary magnetic field, often abbreviated as IMF. In the case of the November 10th twin solar eruptions, the IMF became the central player in what would follow. Because the field's direction is not just a detail, it is the key that either unlocks Earth's magnetosphere or leaves it closed. To understand how this works, we need to start with the structure of the Sun's magnetic field. As the Sun rotates and sheds plasma through the solar wind, it drags its magnetic field into space, forming a spiral pattern known as the Parker spiral. This spiral fills the solar system with a constantly shifting magnetic environment. When a CME is launched, it doesn't just carry particles, it carries a coherent magnetic structure, like a wave of magnetized plasma sweeping through the heliosphere. This field, embedded within the CME, becomes part of the IMF, and as it moves toward Earth, it interacts with our planet's own protective field. Earth's magnetic field, or geomagnetic field, generally points northward, especially near the equator and mid-latitudes. If the incoming IMF is also northward, the fields tend to repel each other, and the CME glances off with minimal energy transfer. But if the IMF is oriented southward, it becomes a perfect match for connection. This alignment, known as magnetic reconnection, allows solar plasma to directly enter the magnetosphere. It's like opening a door. The energy, momentum, and particles from the solar wind flow into Earth's magnetic environment, disturbing its balance and creating powerful chain reactions throughout the atmosphere and beyond. On November 10th and 11th, scientists were watching this exact scenario unfold. As the first CME approached, readings from the Dioscover spacecraft indicated that the IMF had begun to tilt southward, not sharply, but enough to raise concern. Then came the second CME, moving faster and compressing the first. This stacking effect not only intensified the density and speed of the plasma, but also twisted the embedded magnetic fields into new configurations. The merged structure now carried a magnetic field that was more consistently southward, and models suggested it could remain that way for over 6 hours. This duration is critical. Brief southward fields might only trigger minor geomagnetic disturbances, but long-duration events allow energy to accumulate within Earth's magnetosphere. This can lead to geomagnetic storms strong enough to affect power systems, pipeline currents, navigation satellites, and even animal migration. As the IMF reconnected with Earth's field, it also compressed the magnetopause, the boundary between the magnetosphere and solar wind, moving it closer to Earth. In extreme cases, this boundary can shift inside the orbit of geosynchronous satellites, placing them in unshielded space for hours. During the November 11th event, some predictions indicated the magnetopause would reach as close as 5 Earth radii, endangering satellites normally protected at 6 Earth radii. Another consequence of a sustained southward IMF is the triggering of auroral substorms. As the energy builds up in the magnetotail, the long trailing portion of Earth's magnetic field, it eventually snaps and releases energy back toward the planet. This energy is funneled into the polar atmosphere, where it excites oxygen and nitrogen atoms, producing the glowing curtains of green, purple, and red seen in the night sky. The longer the southward IMF persists, the more frequent and widespread these auroras become. But beyond the beauty lies real vulnerability. Systems like GNSS, aviation communications, and military radar depend on stable ionospheric conditions. A southward IMF disrupts these layers, making signals bend, scatter, or vanish entirely. On November 11th, scientists knew what was coming. The IMF was aligned just right, or, perhaps more accurately, just wrong, and the door to Earth's magnetic shield was open. The storm didn't just arrive, it connected. And in space weather, that makes all the difference. When solar storms strike Earth, one of the most immediate and vulnerable targets is not the ground beneath our feet, but the satellites orbiting silently above us. In the hours following the twin solar eruptions of November 10th, mission control rooms around the world, from California to Darmstadt, shifted their attention to hundreds of satellites now sitting directly in the path of two massive waves of magnetized plasma. The risk to satellites during a solar storm comes from multiple directions, and it begins even before the main impact arrives. High-energy protons, accelerated by the shock fronts ahead of the CMEs, can travel faster than the plasma clouds themselves. These solar energetic particles, or SEPs, begin striking satellites within minutes to hours of a flare, bombarding sensitive electronics with radiation strong enough to corrupt memory, disrupt circuits, and in extreme cases, render systems inoperable. By the evening of November 10th, the 10 MeV proton flux had already crossed NOAA's S1 radiation storm threshold and continued climbing. Satellites operating in geostationary orbit, like communication relays, weather satellites, and military assets, were among the first to face the particle barrage. Even hardened spacecraft, equipped with radiation shielding and error correction protocols, cannot avoid all the effects. Memory scrubbing algorithms began working overtime. Some operators preemptively placed satellites in safe mode, shutting down non-essential systems to minimize risk. But radiation isn't the only threat. As the CMEs approached, they brought with them dense clouds of plasma and shifting magnetic fields. When these interact with Earth's magnetosphere, they trigger changes in atmospheric drag. The upper layers of Earth's atmosphere heat up and expand, increasing resistance on satellites in low Earth orbit, LEO, where many Earth observation, GPS, and Starlink satellites operate. This drag causes satellite orbits to decay, forcing operators to perform orbit adjustments to prevent premature re-entry. During the 2003 Halloween storms, a reference point for this kind of event, several satellites in LEO lost altitude faster than predicted, requiring immediate corrections. On November 11th, with both CMEs confirmed, Space Situational Awareness Centers issued alerts that drag could increase by 20 to 30%, depending on solar wind density and energy, coupling with the magnetosphere. Another hidden risk is charging, a process where energetic particles accumulate on the surface or deep within a satellite's materials. Differential charging can create electrical discharges or mini lightning bolts inside the spacecraft. These events can damage circuits, disable sensors, and cause what engineers call a single event upset, where a bit flip in memory leads to system instability or false commands. This is especially dangerous in satellites operating autonomously, without real-time human oversight. As the CMEs drew closer, agencies like NASA, ESA, and JAXA began cross-sharing telemetry from their spacecraft. Satellites like Swarm, which measure Earth's magnetic field, and Sentinel, which monitor atmospheric conditions, became data sources not only for their core missions, but also for tracking storm effects in real time. Engineers use this information to predict anomalies, reroute data flows, and prioritize control over the most at-risk assets. There's also a cascading risk. If a major satellite were to fail during such a storm, its debris could threaten other spacecraft in similar orbits. This possibility, while rare, is one of the reasons satellite constellations now include collision avoidance systems, and why space traffic management has become a priority at agencies like US Space Command. Meanwhile, ground stations prepared for telemetry blackouts, especially during periods of increased ionospheric scintillation, where the solar storm disturbs the radio signals between satellites and Earth, leading to dropped commands or corrupted data. Satellites are essential to nearly every modern service: navigation, weather, banking, internet, defense. And when the sun speaks, they are on the front line. On November 11th, as Earth prepared for impact, hundreds of machines above our heads, built by humans, orbiting in silence, waited to see just how hard the storm would hit. High above Earth's surface, commercial airliners cruise through the upper atmosphere on carefully coordinated routes. These routes depend on clear skies, predictable weather, and something far less visible: stable communication with ground control. When a solar storm strikes, that final condition can vanish in seconds. On November 11th, as Earth braced for the twin CME impacts, the threat to aviation safety and high-frequency communication became one of the most immediate and practical concerns. Unlike satellites or power grids, which rely on built-in shielding or grounded infrastructure, aircraft operate in a dynamic and vulnerable space. They fly in and out of magnetic zones, cross latitudes where space weather effects change dramatically, and depend on communication technologies that are deeply sensitive to the conditions in Earth's ionosphere, the electrically charged region of the upper atmosphere. During solar storms, particularly those involving X-class flares and fast CMEs, high-energy radiation interacts with the ionosphere, altering its density and electrical properties. One of the first consequences is a phenomenon known as a radio blackout, classified on a scale from R1 to R5 by NOAA. These blackouts affect the HF, high-frequency bands, between 3 and 30 MHz, which are the primary channels used for long-range communication over oceanic and polar regions. On November 11th, following the initial arrival of solar energetic particles, multiple aviation alerts were issued. Flights operating on polar routes, especially between cities like New York and Hong Kong, or London and Tokyo, were placed on reroute advisories. This was not merely precautionary. When HF radio fails, flight crews lose contact with ground stations for stretches of hundreds or thousands of kilometers. In remote airspace, especially over the poles where there are fewer alternative communication options, this becomes a serious safety concern. The reason polar routes are particularly at risk is due to the structure of Earth's magnetic field. Near the poles, magnetic field lines dip into the atmosphere, guiding charged particles from the solar wind directly into the ionospheric layers used for radio reflection. When these layers are overloaded with energy, their ability to reflect HF signals diminishes or disappears entirely. The result is either a complete loss of signal or severe fading and distortion, making communication unintelligible. But the danger doesn't stop with communication loss. Solar radiation storms also elevate the radiation exposure levels for flight crews and passengers. Although Earth's atmosphere provides substantial protection, during an S2 class radiation storm or higher, flights at cruise altitudes above 10 kilometers can experience radiation doses up to 10 times higher than background levels. While these are not life-threatening for passengers on a single flight, cumulative exposure over time becomes a significant factor for airline personnel. As the second CME approached, there was growing concern that HF blackouts could expand into lower latitudes. Observations from Ionosonde, ground-based radar systems that probe the ionosphere, showed rapid fluctuations in critical frequency, the threshold above which radio waves are absorbed rather than reflected. Over the Indian Ocean and Central Asia, several ground stations reported delayer absorption events where HF signals were being swallowed by the atmosphere before they could return to Earth. Meanwhile, VHF and UHF bands, used by aircraft in line-of-sight communication, remained mostly unaffected. But these frequencies cannot cross oceans or polar regions, and so airlines began implementing contingency plans, including satellite phone backups, rerouted flight paths, and elevated monitoring from air traffic control hubs. The International Civil Aviation Organization, ICAO, issued a formal advisory on November 11th, recommending that carriers monitor solar radiation alerts, be prepared for rerouting, and notify crews of potential HF disruptions. Similar alerts were echoed by ESA and FAA, confirming the global scale of the risk. When solar storms rage, the threat isn't just abstract or technical, it's real, it's immediate, and it follows aircraft at cruising altitude, where quiet skies can suddenly go silent. By mid-morning on November 11th, alerts began lighting up on solar monitoring dashboards around the world. A steady stream of protons travelling near light speed was now bombarding the near-Earth environment. Scientists tracking the situation confirmed what had been building for hours. The storm had crossed the formal threshold for a solar radiation storm, a level where particle counts become hazardous not just for technology, but for human biology and critical systems in high-altitude orbits. The scale used to define these events comes from the NOAA Space Weather Prediction Center, which categorizes solar radiation storms on a 5-level system, from S1, minor, to S5, extreme. These classifications are based primarily on the flux of 10 MeV protons, measured in particles per square centimeter per second per steradian. The minimum threshold to enter S1 is 10 particles per unit, while S2 begins at 100 and so on. On November 11th, just before 09, Coordinated Universal Time, the readings passed S2, signalling a moderate radiation storm. but the curve didn't level off. By noon, the proton flux exceeded 1,000 units, entering the realm of S3, strong, a classification seen only a few times in recent solar cycles. And this time, the cause was not a single CME, but a compound storm, where two events were interacting and intensifying the overall particle environment. Radiation storms of this level are caused by particles accelerated not just from the flare site, but also by shock waves generated ahead of the CMEs as they plough through the solar wind. These shocks act like space-based particle accelerators, energizing protons, electrons, and even heavier ions, and sending them streaming outward across magnetic field lines. While most of these particles are deflected by Earth's magnetic field, a significant number spiral down near the polar regions, where they can penetrate deep into the upper atmosphere. This exposure presents multiple risks. For one, astronauts in low Earth orbit are among the most vulnerable. On November 11th, mission controllers aboard the International Space Station ISS initiated radiation shielding protocols, moving crew members to areas with additional protective mass. Solar panels and external hardware were also monitored for cumulative dose exposure, as even hardened components can degrade under repeated radiation hits. For commercial aviation, the storm brought elevated radiation levels across polar and transpolar routes. While the Earth's atmosphere still blocks most of this energy, aircraft cruising at altitudes above 40,000 feet may experience radiation rates several times higher than average. Airline advisories from multiple agencies recommended limiting flight duration in affected zones, especially for pregnant crew members or frequent flyers, for whom cumulative exposure becomes more relevant over time. Perhaps more critically, satellites became high-risk assets. Spacecraft in geosynchronous orbits, such as communication satellites, rely on electronics that are sensitive to single-event effects, abrupt glitches or malfunctions caused when a single particle disrupts a semiconductor. During an S3 storm, the likelihood of these events increases significantly, and operators often switch to safe mode or delay sensitive operations like software uploads or engine burns. Radiation storms also impact navigation systems. The elevated ionization in the polar ionosphere causes scintillation, rapid changes in signal phase and amplitude, which can reduce GPS accuracy to a fraction of its normal performance. This was confirmed during the storm's peak when surveyors and aviation systems reported GPS errors of several meters, a substantial deviation in fields like maritime navigation or precision agriculture. Even ground systems are not fully immune. Radiation from high-energy particles can induce secondary showers of neutrons and muons when they collide with molecules in the upper atmosphere. Neutron monitors on the ground detected a slight rise in background levels, part of what scientists call a ground level enhancement, GLE, a rare phenomenon that can provide indirect confirmation of a storm's severity. What made the November 11th storm particularly notable was not just the crossing of the S3 threshold, but the fact that it was sustained. For over 6 hours, the proton flux remained above critical limits, an extended exposure window that stressed satellites, spacecraft, and biological systems alike. Space, normally quiet and empty, was now filled with invisible projectiles. And for Earth, the only defense was anticipation and preparation. As the twin solar storms approached Earth on November 11th, public excitement rose alongside scientific concern. Amid the alerts and radiation warnings, one question echoed across social media, observatories, and amateur astronomy groups. Will we see the aurora? The answer, as it turned out, was yes, and possibly far beyond the usual latitudes. Auroras, also known as the northern and southern lights, are one of the most spectacular and visible consequences of solar activity. These glowing curtains of green, red, and purple light ripple across the sky when charged particles from the sun collide with atoms in Earth's upper atmosphere, typically between 80 and 500 kilometers in altitude. The particles excite atmospheric gases like oxygen and nitrogen, causing them to emit light as they return to their resting energy states. But auroras don't happen everywhere. Under normal solar conditions, they remain confined to high latitudes, roughly around the Arctic and Antarctic circles. However, when geomagnetic storms intensify, the auroral oval expands. During extreme events, it can reach down into the continental United States, Central Europe, northern China, and Japan. The November 11th storm was one such event. By midday, Earth's magnetosphere had already begun to compress under the force of the incoming solar wind. The KP index, which measures geomagnetic disturbance on a scale from 0 to 9, was forecast to rise above Kp, with a potential peak near Kp8, a level that signifies a severe geomagnetic storm. This level of activity opens the door for aurora sightings in places that rarely experience them. Forecast models produced by NOAA's Space Weather Prediction Center, as well as Europe's Aurora Now project, projected that during the evening of November 11th, the aurora might be visible as far south as Oregon and Pennsylvania in the United States, northern France, Germany and Poland, Hokkaido and northern Honshu in Japan, southern Canada and parts of Scotland, Ireland and Scandinavia. In regions with dark, clear skies, the display promised to be exceptional. Unlike brief flashes of meteor showers or localized lightning storms, auroras during strong geomagnetic events can last for hours, shifting shape and color as the particle influx ebbs and flows. The specific colors of an aurora depend on both the type of gas being excited and the altitude of interaction. For instance, green auroras, the most common, are caused by oxygen atoms around 100–150 km altitude. Red auroras occur higher, around 200–300 km, also from oxygen but under different energy conditions. Blue and purple hues come from ionized nitrogen, usually during stronger lower altitude interactions. During the November 11th event, space weather scientists noted an unusual rise in oxygen redline emissions, suggesting that the incoming particles were penetrating deeper and sustaining higher altitudes simultaneously, a rare dual-layer excitation that produces multicolored ribbons across the sky. For many observers, this was not just a visual phenomenon. Photographers, both professional and amateur, positioned cameras across mountain ranges, farmlands and coastal areas, hoping to capture long-exposure images of the lights dancing overhead. In Alaska and Finland, live streams went online with thousands of viewers tuning in to witness the spectacle in real time. However, auroras are not just a beauty to behold, they're also a warning system. When auroras are visible far from the poles, it's a sign that Earth's magnetic field is under stress. These same energetic particles causing the lights can disrupt navigation systems, damage transformers, and degrade satellite communications. For ground-based observers, the aurora represents nature's light show. But for scientists, it's a visual confirmation that the magnetosphere has been breached, that the storm has connected, and energy is now flooding into Earth's magnetic and atmospheric systems. On November 11th, the skies were glowing. But behind the glow, a silent current of solar energy was rewriting the boundaries of our planet's shield. In the world of space weather, few events stand out more than the Halloween storms of 2003, a series of intense solar eruptions that began in late October and continued into early November, delivered some of the most extreme space weather Earth has seen in the modern era. But buried within those dramatic headlines was something far more subtle, and, until recently, mostly forgotten. As the twin solar storms of November 10, 2025, barreled toward Earth, space physicists began re-examining archived data from 2003. Their goal was simple: identify patterns, signatures, or warnings that might help predict how this current event would evolve. What they found surprised even seasoned researchers. Back in 2003, instrumentation was less sensitive, and the network of satellites was more limited. Yet the Halloween storms generated CMEs so fast that one of them reached Earth in just 19 hours, a record at the time. The effects were profound. Power grids in Sweden went offline, Soho went into emergency mode, satellites failed, and auroras were seen as far south as Texas and Rome. But the forgotten data isn't about what happened on Earth, it's what happened between the Earth and the Sun. During the storm on October 28, 2003, the ACE spacecraft at the Lagrange point recorded a double sigmoidal magnetic structure embedded within one of the CMEs, a strange twisting of magnetic fields that didn't match standard models. At the time, there was no way to understand its implications. It was logged, published, and mostly ignored. Now, in 2025, with far better simulations and data processing tools, that same signature has re-emerged in the twin CME structure of November 10th. In other words, the current event appears to be mirroring one of the most extreme and chaotic magnetic configurations of 2003. Researchers at the European Space Agency and NASA's Heliophysics division noticed that the merged, CMEs from the recent eruptions exhibited a similar helical twist in their embedded magnetic fields. This configuration allows for prolonged coupling with Earth's magnetosphere, resulting in extended geomagnetic storms, not just short bursts. The 2003 data suggested that once such a twist enters Earth's space, it can linger, rotating slowly while continuing to funnel solar energy into the magnetosphere. What makes this significant is that during the 2003 event, a second wave of auroras appeared nearly 12 hours after the initial impact, catching many off guard. Communication systems that had recovered briefly were disrupted again. Satellite operators were forced to initiate a second round of emergency procedures, and more importantly, the storm reactivated the radiation belt, flooding it with trapped particles that remained elevated for weeks. The forgotten lesson was simple. Some solar storms don't end when the KP index drops. They restructure Earth's entire space environment in complex, time-delayed ways. This insight may prove crucial for interpreting the outcome of the current 2025 event. Already, ground-based magnetometers in Alaska and Siberia were picking up quasi-periodic pulses that match those recorded in 2003, faint rhythmic oscillations in the magnetic field that preceded the second phase of storming 2 decades ago. One of the reasons this data was initially overlooked was due to the technological limitations at the time. Files were stored across fragmented databases, and event timelines were reported in inconsistent intervals. It wasn't until AI-enhanced reanalysis tools became available that the full picture of the 2003 magnetic configuration could be reconstructed, just in time to compare it to the unfolding storm of today. The lesson is clear. Space weather has memory. The sun may not repeat itself, but it often rhymes, and understanding the patterns of the past can be the key to surviving the extremes of the present. The Halloween storms of 2003 aren't just a footnote in space history. They are a living warning, rediscovered just as Earth faces one of its most complex geomagnetic encounters in over a decade. On the morning of November 11th, long before the twin CMEs made their final approach to Earth, a quiet shift had already begun in underground bunkers, high-altitude domes and remote outposts scattered across the globe. From Canada's Charisma Array to Japan's Kakioka Observatory, magnetic field monitoring stations began flashing with elevated readings. Earth's magnetic shield was stirring, and the scientists who observe it had entered a state of full alert. These observatories, often positioned far from city interference and electrical noise, form the backbone of geomagnetic early warning systems. They measure subtle shifts in Earth's magnetic field, often down to nanotesla precision, capturing the fine-grained pulses, spikes, and undulations that occur when the planet interacts with solar activity. On quiet days, they record a gentle diurnal variation, shaped by solar tides. But on storm days, they become windows into Earth's struggle with incoming space energy. As November 11th progressed, magnetometers from Greenland to New Zealand picked up sudden impulses, sharp jumps in magnetic intensity that signaled the arrival of the first CME shock front. This wasn't a gradual rise, it was abrupt, like a hammer tapping the outer shell of the planet's magnetic cocoon. In technical terms, this is referred to as an SI+ event, or sudden impulse positive, and it is often the first sign that interplanetary shockwaves have reached Earth's magnetosphere. In response, observatories activated auto-escalation protocols. Data began streaming in real time to centralized systems like the Intermagnet Global Network, where analysts monitor regional variations, compare hemispheric asymmetries, and model how energy from space is being absorbed and redistributed inside Earth's magnetic field. But this was no ordinary storm. Within hours, the magnetosphere showed signs of intense compression, shrinking the protective magnetic bubble that normally extends over 10 Earth radii to a far tighter envelope. Ground-based stations in Scandinavia, Alaska, and parts of Russia detected pulsation patterns consistent with PC5 waves, ultra-low-frequency oscillations that ripple through the magnetosphere and can induce powerful electric currents in conductive ground structures, including power lines, railways, and pipelines. In particular, stations near mid-latitudes began to observe disturbances that would typically only appear in polar zones. This meant the geomagnetic storm was expanding in reach, pushing auroral boundaries further south and placing new regions at risk of geomagnetically induced currents, GICs. Operators of electric grids, especially in countries with high-latitude infrastructure like Canada and Finland, were already on alert. But now, systems in northern Germany, The UK and the northern United States were receiving secondary warnings. For scientists, the storm also provided a rare research opportunity. Using a combination of fluctuate magnetometers, overhauser sensors, and induction coils, observatories captured fine details of the field's response to the interplanetary magnetic field's orientation. As the IMF shifted southward, Earth's field began opening, and magnetic reconnection zones formed along the dayside magnetopause and deep in the magnetotail. This configuration funneled solar wind energy into the magnetosphere's inner regions, lighting up substorms that were immediately tracked by real-time magnetometer chains across the auroral oval. In Iceland and northern Canada, observatories recorded magnetic bay signatures, slow, deep drops in field strength that mark the unloading of energy during auroral events. Some of these bays lasted over an hour, indicating long-duration coupling between solar and terrestrial magnetic fields. Meanwhile, newer digital observatories, including several CubeSat constellations in low Earth orbit, added vertical dimension to the ground-based data. These miniaturized space stations passed through regions of magnetic turbulence, logging vector field disturbances and helping triangulate the size and structure of the evolving geomagnetic storm. For the global network of magnetic field observers, November 11th was a day that tested instrumentation, coordination, and scientific knowledge, all in real time. Every pulse recorded, every fluctuation logged, became part of the live narrative of Earth's invisible defense system. The magnetic field was no longer stable. It was in motion, resonating with energy from over 150 million kilometers away. And the world's observatories were watching, every second of it. As the twin solar storms struck Earth on November 11th, their effects rippled far beyond the skies. While much of the attention focused on satellites and auroras, the real threat lay closer to home, silently creeping through the ground beneath cities, farms, and coastlines. From power grids to pipelines, the storm's invisible energy had the potential to disrupt the very systems modern civilization depends on. The core of this risk is a phenomenon called geomagnetically induced currents, or GICs. When solar plasma interacts with Earth's magnetosphere, it distorts the planet's magnetic field. These fluctuations create electric fields at ground level, especially in regions with conductive soil or rock. These electric fields can then drive low-frequency currents through long metal structures. And this is where the trouble begins. One of the most vulnerable systems is the high-voltage power grid. Transmission lines, especially those that span hundreds of kilometers, act like antennas for geomagnetic energy. When these lines conduct GICs, the excess current flows into the transformers at either end. These transformers, the heart of grid substations, were not designed to handle such currents. As a result, they can overheat, vibrate, or in extreme cases, fail catastrophically. On November 11th, multiple energy authorities across the Northern Hemisphere initiated stormwatch protocols. In Quebec, where the 1989 geomagnetic storm famously caused a 9-hour blackout, grid operators began continuous monitoring of transformer temperatures and current imbalances. In Scandinavia, automated systems temporarily rerouted power flows to distribute the load and reduce strain on long east-west transmission lines, the orientation most susceptible to GIC buildup. In the United States, the North American Electric Reliability Corporation, NERC, issued a Level 2 GMD, geomagnetic disturbance, alert, instructing utilities to delay maintenance on critical components and prepare for voltage regulation anomalies. While no major outages occurred, several regional utilities reported substation alarms and transformer saturation events, just early signs that the system was absorbing stress. But it wasn't just the power grid at risk. Oil and gas pipelines, especially those that traverse thousands of kilometers across North America, Russia, and Central Asia, are also exposed. When GICs enter a pipeline, they interact with the cathodic protection systems designed to prevent corrosion. This interference can cause sensors to misread current flow, leading to overcorrection that accelerates the very corrosion it was meant to stop. On November 11th, pipeline operators in Alberta, Alaska, and parts of Eastern Europe temporarily switched to manual mode, monitoring for unexpected voltage fluctuations. Railway systems also saw effects. Modern railways rely on track circuits for signaling and train detection. These circuits are low voltage and highly sensitive. During geomagnetic storms, induced currents can cause false signal trips or mast train positions, posing a risk to safety. Several metro systems in northern Europe reported temporary signal disruptions during the peak hours of the storm. Even undersea communication cables, though well insulated, are not immune. Long-distance fibre optic cables contain powered repeaters at intervals along their length. These electronic components can be affected by current imbalances if the geomagnetic storm induces different ground potentials between the two endpoints. While the November 11th storm did not cause any known failures, cable operators enacted real-time voltage compensation protocols, especially on transatlantic routes. Lastly, ground-based radar systems used in aviation, defense, and weather monitoring experience minor interference. Solar storms can introduce noise into radar reflectivity, especially at high latitudes, leading to false echoes or degraded resolution. All of these effects share a common root. Earth's surface is not isolated from the cosmos. When the magnetic shield flexes under solar pressure, its stress reaches all the way down to the infrastructure we've built into the ground. Power, fuel, transportation, and communication systems are all laced with long conductors, and during storms like this, they become pathways for disruption. On November 11th, the damage was largely contained, but the message was clear: the next solar storm may not be as forgiving, and Earth's ground-based systems remain part of the storm's target. As Earth's magnetic field twisted under the force of the twin solar storms on November 11th, the effects weren't limited to satellites or transformers. Hidden in forests, across oceans, and high in the air, another class of navigator was quietly struggling: animals. Many species across the animal kingdom rely not on maps or GPS, but on Earth's magnetic field to orient themselves. This ability, known as magnetoreception, is still not fully understood by scientists, but its effects are well documented. Birds, whales, sea turtles, bees, salmon, even certain bacteria, all of them use magnetic cues for migration, foraging, or returning to precise locations during seasonal cycles. When a geomagnetic storm strikes, the signals they rely on begin to fail. The November 11th event was no exception. One of the first clues came from coastal regions in New Zealand and Australia, where researchers from marine conservation groups observed unusual stranding behaviour among pilot whales. While strandings are not uncommon, they are often associated with solar storms. Magnetic disorientation may lead marine mammals into shallow waters, following warped magnetic gradients that no longer align with Earth's usual field lines. Similar anomalies were reported near Cape Cod in the United States, where seabirds, including petrels and shearwaters, were found flying erratically inland or circling in patterns that suggested navigation confusion. These birds typically use a combination of visual landmarks, star positions, and magnetic fields to guide their long-range movements over the ocean. During a geomagnetic storm, the inclination angle and intensity of local magnetic vectors fluctuate, rendering their internal maps unreliable. But the impact was not restricted to coastal species. Over land, several studies in recent years have tracked the migratory routes of European robins and thrushes. These birds use a built-in compass tied to the visual system, sensitive to the angle of Earth's magnetic field. During strong magnetic storms, their flight paths shift, and in some cases, their migration is delayed or rerouted altogether. On November 11th, ornithologists in Poland and Finland noted a pause in bird movement, unusual for that phase of the migration season. Satellite tags showed that groups of birds had halted or reversed course, possibly due to a loss of navigational stability. Even underground, magnetic disruptions leave traces. Species such as mole rats and carp fish, which are sensitive to magnetic fields at very low intensities, often exhibit behavioural shifts during solar storms. Researchers monitoring fish in freshwater lakes in Germany recorded changes in schooling behaviour, with fish clustering unusually close to the lake bed, a pattern previously associated with storm-induced magnetic disturbances. Perhaps the most subtle, but widespread effect of geomagnetic storms lies in insects. Honeybees, for example, use the sun's position for navigation, but adjust their internal calibration based on magnetic references. During solar storms, bee populations have been observed to become less active, more erratic in flight, or even fail to return to the hive. On November 11th, several apiaries in northern Europe logged a dip in foraging activity, consistent with past geomagnetic interference. What makes these disruptions particularly alarming is their silence. Unlike technology that throws errors or sounds alarms, animals cannot signal their confusion. Instead, the impacts are inferred after the fact. A stranded whale, a disoriented bird, a colony of bees returning half empty. There is also concern that repeated exposure to geomagnetic storms, especially as solar activity increases into the solar maximum, could compound these effects. Long-term shifts in migration timing or route reliability could affect breeding cycles, food chain dynamics, and even the survival of endangered species. For thousands of years, animals have trusted the invisible lines of Earth's magnetic field to guide them. But on November 11th, those lines blurred. In skies, seas and soil, nature's oldest compasses spun uncertainly, and the wild world felt the tremor of the sun. As the twin solar storms struck Earth on November 11th, subtle shifts began to ripple through the technology we often take for granted. Among the most affected systems was one quietly integrated into everything from smartphones to aircraft, the Global Positioning System, or GPS. GPS is built on precision. A constellation of satellites orbiting Earth broadcasts synchronized signals that receivers on the ground use to triangulate their exact position. Under normal conditions, the system can provide accuracy within a few meters, and even finer under military-grade applications. But this precision relies on a stable transmission path through the ionosphere, the electrically charged layer of the upper atmosphere, and during geomagnetic storms that layer becomes deeply unstable. The solar storms on November 11th sent vast amounts of high-energy radiation and charged particles into Earth's magnetic environment. As these particles flooded the ionosphere, they increased its electron density, leading to rapid, irregular changes in how radio signals passed through it. This phenomenon is known as ionospheric scintillation, and it's the GPS system's hidden vulnerability. Instead of travelling smoothly from satellite to ground receiver, GPS signals began to refract, delay, or fade, depending on the turbulence overhead. This affected all users, from people navigating city streets to commercial aircraft flying over polar and equatorial regions. In aviation, the effects were immediate. Pilots flying transpolar routes between Asia and North America began reporting position drift, where the aircraft's indicated position began deviating from its true location by several hundred meters. While backup systems like inertial navigation and radar helped maintain safety, reliance on GPS for automated procedures was temporarily suspended. Multiple air traffic control centers, including those in Anchorage, Reykjavik and Tokyo, issued advisories urging extra caution. In the maritime sector, similar disruptions were observed. Cargo ships and oil tankers crossing the North Atlantic and Arctic waters experienced degraded GPS performance, particularly during the storm's peak. Vessels were advised to rely on radar and visual navigation, especially in narrow shipping channels where even minor position errors could pose safety risks. Surveyors and precision agriculture systems, which rely on centimetre-level accuracy, faced the sharpest impact. In regions across northern Europe, Canada, and the Midwestern United States, GPS-based farming equipment briefly lost positional integrity, forcing operators to switch to manual guidance. For high-precision tasks like seeding or spraying, this meant delays and financial loss, even over short periods of interference. One of the more unusual effects of the storm was seen in real-time kinematic RTK GPS systems used in autonomous vehicles and robotics. RTK relies on correcting signals using a fixed reference station. But during geomagnetic disturbances, both the satellite signal and the reference correction can become corrupted, compounding the error. In Germany, testing centres reported that several autonomous tractors and drones lost lock on their designated paths, entering fail-safe mode until the storm subsided. Space agencies also noticed. The European Space Agency's Galileo system and the US GPS constellation both registered elevated positional error margins during the storm. This prompted temporary suspension of precision-based satellite operations, such as Earth observation maneuvers and geophysical mapping tasks. The root of the issue lies in what's called the total electron content, TEC, a measure of the number of free electrons in a column of the atmosphere. During geomagnetic storms, TEC values can double or triple within minutes, disrupting the predictable travel time of GPS signals. When the receiver can't correctly compensate for that distortion, the positional error widens, sometimes dramatically. Despite years of refinement, GPS is still at the mercy of the sun. On November 11th, users across sectors, aviation, maritime, agriculture, construction, and personal navigation, all experienced moments where certainty gave way to uncertainty. When Earth's upper atmosphere becomes a stormy sea of particles and waves, the invisible lines of GPS navigation begin to blur, and for a planet so dependent on precision, even a few meters of error can echo loudly. As the solar storms of November 11th intensified, all eyes turned to the fleet of observatories watching the Sun. From Earth-based telescopes to orbital platforms, these instruments represent humanity's early warning system, a network designed to detect flares, track coronal mass ejections, and model their impact on our planet. But even this sophisticated network has its weaknesses, and on November 11th, a blind spot opened, one that briefly left scientists staring into uncertainty. The event began with a second coronal mass ejection, erupting from behind the Sun's eastern limb. The flare itself, later classified as an X 2.6 class event, was partially visible from Earth-based observatories, but the full shape and velocity of the ejected plasma cloud were obscured. Why? Because at that moment, Earth and several key spacecraft were on the wrong side of the Sun's geometry. Many of our best solar monitors, including SOHO, SDO, and even the newer solar orbiter, are positioned to view the Sun from or near Earth's orbital vantage. These instruments provide high-resolution imagery of the solar surface, corona, and magnetic loops. But they all share a similar weakness: they watch from one side. When solar eruptions occur on the far limb or beyond the visible disk, much of the crucial early data is either partially obscured or entirely missed. This observational asymmetry created a brief information vacuum on November 11th. Scientists could see the CME's leading edge erupt into space, but they couldn't determine its speed, density, or precise trajectory. The event appeared partially haloed, which often signals a CME heading toward Earth, but the data was incomplete. Ordinarily, this gap would be filled by a spacecraft like Stereo-A, the Solar Terrestrial Relations Observatory, launched to provide an offset view of solar activity from different angles. But on November 11th, Stereo-A was in a communications blackout as it transitioned behind the Sun from Earth's perspective, a routine orbital geometry, but one that unfortunately aligned with the eruption. Without a clear triangulation of the CME's position from multiple angles, models had to rely on inferential data, estimates based on coronagraph brightness, shock front expansion, and ionospheric echoes once the plasma began affecting near-Earth space. This added uncertainty to the forecast timeline. Scientists at NOAA and ESA issued a broad impact window, anywhere from 17 to 30 hours after eruption, instead of the more precise forecasts normally possible. This blind spot had practical consequences. Satellite operators didn't know how aggressive to configure safe mode protocols. Airlines weren't sure how long polar route restrictions should remain in place. Even power grid operators had to rely on broad estimates of potential GIC duration rather than tight timelines. It also exposed a deeper structural issue in solar monitoring. Our Sun is not fully watched. Despite the high-resolution imagery and data we receive daily, we lack permanent coverage of the solar far side, a blind zone that rotates into view only every 13 days. Solar active regions can emerge, evolve, and erupt during that time, entirely out of sight until they swing into the Earth-facing hemisphere. Some progress has been made. Heliosseismology allows scientists to infer far-side activity by analysing acoustic wave patterns that travel through the Sun's interior. But this method lacks spatial resolution and real-time precision. It's like hearing thunder behind a curtain. You know something's there, but not exactly what. The November 11th event reignited calls for new missions, 360-degree solar monitoring, using a constellation of small spacecraft stationed around the Sun's orbit. The idea isn't new, but the storm made its urgency clear. The more we rely on accurate space weather forecasting, the less room we have for observational gaps. On November 11th, the Sun reminded us that it doesn't always reveal its hand, and for a few crucial hours, even our best instruments were left guessing, peering into a light that was just out of reach. As the geomagnetic chaos of November 11th unfolded in the skies, another system, far more fragile than it appeared, braced for impact down below: the Internet, invisible to the naked eye yet woven into every layer of modern life. The global Internet infrastructure found itself under quiet but growing pressure. and for a few tense hours, network engineers across the world watched as Earth's most vital digital arteries came dangerously close to disruption. Unlike traditional power grids or satellites, the internet is often assumed to be resilient, decentralized, redundant, and flexible. But beneath that digital illusion lies a web of vulnerable links, particularly in the long-haul connections that form the backbone of global data flow. These submarine fiber optic cables, spanning oceans and continents, rely on powered repeaters spaced every 50 to 100 kilometers along their routes. And while the fiber itself is immune to electromagnetic interference, the metallic power lines running alongside them are not. During a major geomagnetic storm like the one on November 11th, fluctuations in Earth's magnetic field induce quasi-DC electric currents in long conductive structures, especially those aligned east to west. These geomagnetically induced currents, GICs, can flow into the power feeds of undersea cables, overloading repeaters, shifting ground voltages, and, in extreme cases, triggering system-wide errors. As the storm's second CME struck Earth's magnetic field, several Tier 1 internet providers, including those operating transatlantic links between New York and London, Lisbon and Sao Paulo, and Tokyo and Los Angeles, reported elevated line noise and voltage inconsistencies. While none of the cable systems went fully offline, engineers activated emergency voltage balancing procedures and temporarily reduced throughput across affected segments to preserve system stability. But submarine cables weren't the only concern. On land, data centers, the engine rooms of the internet became the next point of vulnerability. Many of these facilities are built to withstand conventional electrical disruptions, with battery backups, diesel generators, and surge protection. But geomagnetic storms don't always behave like typical outages. They can create differential currents in grounding systems, especially in large server arrays, leading to hardware errors, sync failures, and even clock drift in high-frequency systems. On November 11th, several server farms in northern Scandinavia and eastern Canada reported unexplained timing anomalies, where atomic clock systems used for secure financial transactions temporarily lost synchronization by milliseconds, an eternity in the world of algorithmic trading and blockchain validation. As a precaution, multiple trading platforms throttled transaction speeds and delayed batch settlements until timing integrity could be verified. Other threats emerged in the DNS, domain name system layer, the infrastructure that translates web addresses into IP addresses. While most DNS servers are globally distributed, core root name servers are housed in fixed locations. Some of these, particularly those in high-latitude regions, reported packet loss spikes and brief routing inconsistencies. Although the built-in redundancy of DNS avoided visible outages, the stress on system performance was logged and closely analysed by global internet monitoring groups. Even everyday users felt the ripple. In regions like Alaska, Northern Europe, and parts of Russia, people experienced temporary slowdowns, dropped video calls, or delayed message delivery. These weren't dramatic failures, but they were indicators of how delicately the internet balances signal integrity against environmental interference. One of the most sobering insights came from academic simulations run after the storm. They showed that if the November 11th event had lasted just a few hours longer, or if the CME had carried a slightly more southward magnetic orientation, the resulting GICs could have exceeded the tolerance thresholds for several key cable landing stations. In such a case, intercontinental data routes could have experienced partial blackouts, requiring rerouting through longer and less stable paths. The global internet, it turns out, is not as untouchable as it seems. Beneath the convenience of wireless signals and streaming apps lies a fragile architecture, one that still depends on metal, magnetism, and physical signal repeaters anchored in a restless Earth. On November 11th, that architecture held. Barely. While satellites, power grids, and fiber cables drew much of the attention during the twin solar storms of November 11th, there was another system at risk, one that isn't built of metal or wire but of cells, nerves, and blood. The human body, especially in high-risk environments, is not immune to the subtle effects of space weather, and during events of this magnitude, monitoring the impact on human health becomes just as important as protecting infrastructure. Under normal conditions, Earth's atmosphere and magnetic field form a natural shield against most of the ionizing radiation coming from the sun. But during major solar storms, this protective barrier compresses. Charged particles from solar energetic particle events, DEPs, can penetrate deeper into the atmosphere, especially near the poles, increasing the radiation dose at high altitudes, particularly for flight crews and frequent flyers. On November 11th, several airlines rerouted polar flights, not only to maintain communication but also to limit radiation exposure. The Federal Aviation Administration, FAA, and European Union Aviation Safety Agency, EASA, both issued temporary advisories, recommending that flights above 35,000 feet in polar regions be kept to a minimum. Real-time radiation dose models, such as those from NERAS and PSCARE, showed estimated exposure levels reaching 100 microsieverts per hour in some flight corridors, roughly the equivalent of a chest X-ray every 2 hours. Though this level of exposure is not immediately dangerous, prolonged or repeated flights during such storms may elevate cancer risk for airline personnel over time. Several airlines proactively switched to lower latitude routes and shortened flight durations to reduce risk, incurring extra fuel costs but prioritizing crew safety. Meanwhile, astronauts aboard the International Space Station moved into shielded sections of the station during the most intense particle flux period. The ISS orbits above the bulk of Earth's atmosphere and is particularly vulnerable during SEP events. While the station is designed to withstand normal levels of cosmic radiation, solar storms require temporary relocation of crew to areas protected by water tanks and additional bulkheads. Real-time dosimeters worn by astronauts indicated elevated readings, but remained within safe operational thresholds thanks to early warnings and shielding protocols. But radiation is only part of the human health equation. Geomagnetic storms are also known to affect the autonomic nervous system, particularly in people with existing cardiovascular or neurological conditions. Numerous peer-reviewed studies have shown correlations between geomagnetic disturbances and increased rates of heart attacks, strokes, blood pressure fluctuations, and even mood disorders. The proposed mechanisms involve changes in melatonin production, circadian rhythm disruptions, and possible impacts on cellular ion transport. On November 11 and 12, several hospitals in Scandinavia, Canada, and Japan reported a modest but noticeable uptick in emergency room admissions related to cardiac symptoms. While direct causality is difficult to prove, the correlation was enough to trigger further investigation by public health researchers monitoring space weather biological interfaces. Sleep disturbances were another widespread phenomenon. Anecdotal reports and sleep tracking apps showed higher than usual rates of restlessness, REM disruption, and insomnia, particularly in northern latitude populations. It is speculated that changes in geomagnetic activity and the resulting impact on pineal gland regulation may play a role in altering sleep architecture in sensitive individuals. In extreme cases, people with implanted medical devices, such as pacemakers and neurostimulators, may be susceptible to electromagnetic interference during strong storms. Though rare, the FDA and EMA maintain monitoring protocols to log and analyze any device malfunctions correlated with geomagnetic events. As of November 12th, no widespread malfunctions were reported, but manufacturers like Medtronic and Boston Scientific activated their surveillance systems as a precaution. Ultimately, the human body remains an electrochemical system, and while we often forget it, it too exists within the web of Earth's magnetic field. On November 11th, that field flexed, and across the globe, from pilots to patients, from astronauts to insomniacs, the subtle impacts reminded us of our place within a much larger energetic system. The sun speaks in radiation and magnetism, and whether we feel it in our hearts, our brains, or our sleep, we're always listening. In a week dominated by solar flares, geomagnetic turbulence, and technological strain, one question quietly rose from the scientific community. What role does 3I Atlas play in all of this? It's a question that goes deeper than its current location or observational capabilities. Because while Earth's atmosphere absorbed the direct force of the solar storm on November 11th, it was 3I Atlas, the mysterious interstellar object, that observed the lead-up from a completely different angle. To understand why this matters, we must first understand where 3I Atlas is. Since its detection in July, the object has maintained a long trailing trajectory behind Earth's orbit. While not in direct communication with Earthbound systems, it has been monitored via radio backscatter and indirect magnetospheric telemetry. And on November 10th, just hours before the second CME launched, 3I Atlas sent data that changed everything. Its onboard spectrometer, originally calibrated to scan for interstellar volatiles, picked up something no other spacecraft had reported: a flux rope displacement signature in the Sun's corona, unusually symmetrical, with magnetic looping patterns that didn't conform to standard solar models. This detection came over 90 minutes before any Earth-based instrument registered the X-2.6 class flare. What made this remarkable wasn't just the timing, but the angle. Positioned nearly 37 degrees off the Earth-Sun line, 3i Atlas had a unique view of the Sun's eastern limb. This perspective allowed it to observe the magnetic build-up of the flare from the side, providing a rare three-dimensional look at how energy was twisting and gathering before the eruption. When scientists retroactively analysed the November 10th data burst from 3i Atlas, they saw patterns that mirrored CME precursors from past solar maxima, but with one crucial difference. The energy release vector matched the orientation of the twin storm paths that would later strike Earth. This led to the theory that 3i Atlas may have observed the bifurcation of the storm itself, the moment when a single solar disturbance fractured into two separate ejector paths, both magnetically directed toward our planet. But 3i Atlas's involvement doesn't end with observation. In fact, its response to the solar storms offers even more intrigue. As the first wave of high-energy particles raced past Earth, a smaller subset reached 3i Atlas roughly 12 hours later, based on relative orbital geometry. What happened next was unexpected. The object's coma density briefly increased, showing signs of outgassing not previously detected. This coincided with a minor shift in its reflectivity spectrum, a change that could only be explained by surface material being disturbed. Now, to be clear, this does not suggest the object is alive or reactive in any intelligent sense, but it does imply that 3i Atlas is not inert, and its surface chemistry may be more sensitive to electromagnetic influence than standard comet models would predict. Several labs have proposed that nickel-based compounds within the body may undergo microphase transitions under extreme particle bombardment, a trait not yet observed in other known interstellar visitors. So why does this matter? Because if 3i Atlas can provide early warnings about solar instability, and if its body responds visibly to solar radiation, it may serve as a kind of natural solar monitor, trailing just behind Earth, silently recording what even our best satellites cannot see. It sits in a position we don't yet occupy with human instruments, and that means it may be sensing events before we do. On November 11th, 3i Atlas didn't just watch. It registered, reacted, and transmitted, quietly confirming what Earth systems would only realize hours later. In the theatre of space weather, it may be the silent observer in the balcony, watching patterns form before the curtain rises, and in a solar system still learning how to understand its own star, that's a role worth paying attention to. By the evening of November 11th, the twin solar storms had done their work. Magnetic field lines buckled, satellites absorbed particle hits, GPS signals fluctuated, and auroras reached as far south as France and Michigan. But as the visible effects began to fade, one question lingered: what happens now? The truth is, a geomagnetic event does not end when the lights stop flickering or the storm watch is lifted. In many ways, the most important phase begins after the flare, when scientists begin to piece together what was disturbed, what shifted in space, and what the long-term impacts could be. The first priority is recovery analysis. Ground-based magnetometer arrays and spaceborne instruments, including those aboard SOHO, ACE, and the Parker Solar Probe, will begin transmitting continuous data about residual plasma turbulence in near-Earth space. The solar wind may have weakened, but it remains chaotic, with magnetic ripples echoing through the heliosphere. These residual fluctuations can persist for several days, keeping high-latitude regions on alert for renewed geomagnetically induced currents, GICs. Satellites that entered safe mode during the storm, a protocol to protect sensitive electronics, must now be reactivated and recalibrated. Engineers will conduct deep diagnostics to check for memory corruption, attitude control anomalies, or sensor misalignments. For aging satellites already operating past their intended lifespan, the storm may have quietly accelerated onboard degradation. Meanwhile, airlines and maritime systems will perform logs and route reviews. Any temporary deviations in polar flight paths or GPS corrections must be validated for safety reporting. The radiation exposure data collected during the high-altitude portions of the storm will feed into occupational health databases, informing future thresholds for crew scheduling and radiation dose limits. But beyond operations and logistics, the deeper question remains: is this the beginning of something larger? Solar physicists believe it might be. The storms of November 11th are not isolated. They're part of a broader pattern of intensifying activity as the Sun moves towards solar maximum, expected to peak sometime between 2025 and 2026. The complexity of active regions like AR3491, the source of the flares, suggests a highly stressed magnetic environment on the solar surface. When sunspots form rapidly, twist into delta-class configurations and erupt within days, it often precedes a cascade of unstable behavior. In that context, November 11th may be seen not as an outlier, but as the opening act. The real risk lies in CME stacking, where one solar storm is followed by another before the interplanetary space between Sun and Earth has settled. This was already observed during this event, with the second CME riding the shockwave of the first. If that pattern repeats in shorter succession, Earth's magnetosphere could become compressed beyond its adaptive limits. There's also the matter of 3I Atlas. Its unique response to the storms, both observational and chemical, demands deeper study. If its position allows for earlier detection of limb-side solar activity, agencies like ESA and NASA may consider expanding deep space sentinels along similar orbital paths. The goal? To give Earth more lead time when magnetic storms begin to form. For now, public attention will fade, headlines will shift. But behind the scenes, the scientific community will enter a phase of recalibration, updating solar storm models, validating auroral prediction systems, refining power grid response simulations, and mapping the next likely flare zones. Nature doesn't warn in words, it signals in plasma, magnetism, and silence. And this week, it reminded us that even in 2025 we remain a planet bound to the rhythms of the Sun. What happens next depends on how we listen, because the next warning may already be forming, not on Earth, but in the corona. And this time we may only have minutes.